Okay, we are almost done. This is your last example of lesson 2.3. I know there's been a lot, but I wanted to give you a bunch of the different scenarios that you could see. Okay, so example 2.3.5 says block A has a mass of 4.2 kilograms and is suspended from a vertical string, as shown in figure 10. The string passes over a pulley and is attached to block B that has a mass of 1.8 kilograms. If the pulley and the surface of the ramp are essentially frictionless, calculate the acceleration of the blocks and the magnitude of the tension in the string. Okay, so the first thing we need to look at is I'm going to draw a free body diagram of both our blocks. Okay, so block A is 4.2 kilograms, and block B sits on an inclined plane. Sorry, that's a terrible line. Let's redraw that. Sits on an inclined plane that has an angle of 32 degrees. Okay. And this is 1.8 kilograms. Okay. So let's draw our forces, because the first thing we need to do is figure out which way these objects are going to move based on their free body diagram. Okay, so we know we're going to have some force of tension that acts up in this direction, and then the only other force that's pulling block B down is going to be the force of gravity. Okay, same over here. We know we have some force of tension that's going to act up in this direction, right? And remember, tension is equal. So these two are technically going to be equal to each other, just in opposite directions. Okay, and then the only other force that's acting on our block is we have the normal that acts off of the surface, and then gravity that is acting straight down. I can then break gravity down into my y component and my x component. Okay. Now, in order to determine which way it moves, what you want to do is actually think about the acceleration. So if there was no force of tension here, what would the rate of acceleration be for this block? Well, it would be moving at 9.8 meters per second squared down in this direction. For this block, if there was no force of tension, okay, we know it's going to come down the ramp in this direction. Why? Because of the force of gravity here. Okay, and if we look at it, the one force that's going to act in that direction is the force of gravity in the x direction. So if you think about force of gravity in the x direction, the mass hasn't changed. What's now changed is the acceleration rate, which is now a sine theta, which means that you're looking at 9.8 meters per second squared times sine theta. So this number right here is definitely less than 9.8. Okay, so because this acceleration value here is less than 9.8, I know then that this block is actually going to move in this direction, which means that this block is going to move in this direction. Okay, and the reason I do that is to really set up our FNet formulas for each block in terms of their direction of motion, right? So if this is the FNet, or if this is the direction of motion and we know it's accelerating, that's the direction of the FNet. Same up here for this block, okay? And then what we're going to do is we're going to actually now start to create equations for each of our blocks, okay? So for block A, our FNet formula is going to look like FG acts in the same direction as my FNet, so I'm taking away that force of tension. Okay, remember what F net is equal to. F net is just equal to a mass times an acceleration. Gravity is a mass times gravity. And then force of tension is really what we need to solve for. Okay? That's really as far as I can go with block A. Let's do the same thing with block B and see what we get. So for block B, I'm going to ignore this y direction because we're not really looking at it. We know in the y direction that this force of normal has to equal this force of gravity in the y direction, otherwise it would accelerate right through the ramp. Okay, so in terms of the F net, the force that's actually going to pull this block forward is the force of tension. And then the force that's going to act against it is that force of gravity in the x direction. Okay, again, I'm going to make my substitutions. F net for the B block is just going to be the mass of that block times acceleration. Force of tension is what we don't know. And then Fgx is the force of gravity times, notice you're across or opposite that angle, so I'm doing sine theta. So I'm going to simplify it one step further. And this is what we get. Okay? Now, how do we solve for the acceleration? Remember, because now we have two equations where the acceleration and the force of tension are both unknown. Okay, remember, because they're tied together, there's two things that we know are going to be equal. Those two things that are going to be equal to each other are, they are going to accelerate at the same rate, and that force of tension that they experience is going to be the same as well, right? Because they're attached to the same rope. The force of tension remains constant throughout the rope. The pulley just changes the direction of it. So if that force of tension remains equal, then the acceleration is going to be the same for both blocks. So in order to solve for that acceleration, what I'm going to have to do is rearrange both of these equations to solve for the force of tension. So in B, the force of tension is simply going to be equal to F net plus this force of gravity in the x direction. If I go back to my x direction and I want to rearrange, what I end up with is the force of tension equals gravity subtract F net. Okay? Now, you've isolated both of your formulas for Ft. We know that's equal. So what I can do is I can now set these equations equal to each other. Notice this is a lot like our question last year with the pulley and the carts on the table. Now we're just looking at an inclined plane. Okay, so the mass of A times gravity minus the mass of A times acceleration has to equal the mass of B times acceleration plus the mass of B times gravity times sine theta. Okay, I'm going to collect the accelerations on the right side of the equal sign. So I really get the force of gravity acting on the block minus that x component of the force of gravity that acts on our block on the ramp has to equal mass B times acceleration plus mass A times acceleration. Okay, so simplify one more. Okay, and you'll notice what you end up with on the right side of the equal sign is if I factor out the acceleration, I just get those masses added together. So acceleration is just going to be equal to gravity on block A minus the x component of gravity on block B, all divided by the combined mass of B plus A. And then once we have that, we can actually just plug everything in and go to solve. Okay, so mass A was, I just got to go up to double check, 4.2. So we get 4.2 kilograms times 9.8 meters per second squared minus 1.8 kilograms was the mass of B times 9.8 meters per second squared times the sine of, what was it, 32 degrees, sine of 32 degrees. Okay. And that all gets divided by, that's a terrible line, all gets divided by the combined mass of 4.2 kilograms plus 1.8 kilograms. Okay, we'll simplify here. Okay, so I get 41.16 newtons minus 9.35 newtons all over 4.2 plus 1.8 is 6 kilograms. Okay, so this simplifies to 34.81 newtons all over 6 kilograms. Okay, gives us an acceleration rate of 5.8016 meters per second squared. Okay, so there's the first part. We know our rate of acceleration now is that. Now to solve for the force of tension, I'm simply just going to plug it back into one of these formulas. Okay, this one's probably the easiest to deal with because we don't have any components. So I'm going to plug it back into that one to solve for the force of tension. Okay, so for that formula, we had F net equals force of gravity minus that force of tension, right? So when we rearranged, we had force of tension was equal to, well, just look at what you had on the left side of the equation. We had mass A times gravity minus mass A times acceleration. So I'm going to factor out the mass, and then the acceleration is simply gravity minus acceleration. Okay, so the mass of A was 4.2 kilograms. Gravity is 9.8 meters per second squared. And we're subtracting this 5.8016 meters per second squared. So I get 4.2 times 3.9983. Okay, and that comes out to 16.793 newtons. Okay, so therefore, the rate of acceleration is 5.8 meters per second squared. And the force of tension in the rope is 17 newtons. Okay, so notice very similar to those problems we did last year with a cart on a table. The only difference is now one object is on an inclined plane, so we have to use that slanted axis. Okay, this is Wanny signing off, and may the force be with you.